Probability distribution. Okay. Well, after this, you can tell me how this compares to the others. So let's take a simple example with some dice. Let's suppose we roll 2 dice and add the numbers we see.
Are they D6s?
Just D6, fair dice, 2 normal balanced 6-sided dice. And we add the numbers. So the experiment is that you do this and you write down only the answer when you add the numbers. And you see what kind of results can I get. So the possible outcomes are what? What is the smallest number I can get?
2.
I only write down the 2. I see the result, I add the numbers, I write down on my clipboard 2. I can't get any lower than 2. So what I write down on my clipboard as the outcome doesn't necessarily show the rolls that resulted in that. Can I get a 3?
Yes.
4?
Yes.
5?
Yes.
6?
All the way to 12.
How high does this go?
12.
12. So yes, the 2 can only be obtained if I roll 2 1s. The 12 can only be obtained if I roll 2 6s. But the stuff in the middle can happen in multiple ways. But the outcomes, based on the description of what I do, the outcomes are only 2 to 12. Then we can say the probability of outcome 2 is, well, it's a fraction. But when I count the fraction, I need to look at the pairs. Here I need to look at the pairs of numbers I can get. Let's say one's red, one is blue. Because not all of those 2 to 12 numbers are equally likely. I can only calculate a probability if the outcomes are equally likely. But the pairs, if I actually look at the dice results, those are all equally likely. So in order for me to get this probability fraction, I need to look at it a little bit differently, still trying to get one of those outcomes, a 2 in this case. So there are still 36 possible pairs, and only one of them is going to give me, only the 1-1 roll is going to give me the outcome of 2. So there are rolls and things that are happening that result in these outcomes. And there's only one way of getting an outcome of 2. But if I look at the next one, for example, and for these dice, we just list the options. It's not anything fancier than that. The probability of the outcome 3, looking at the pairs, out of the 36 that are possible, how many of the pairs will give me an outcome of 3? Well, it's going to be 1, 2, or 2, 1. Is there anything else that I could get? Those are the only ones. So 2 out of 36 will be the probability of the outcome being 3. And you see, they're not equally likely. I am twice as likely to get an answer of 3 when I add up the numbers than I am to get an answer of 2. And we can keep going like this, but the words are getting a little bit tedious to always write down the same thing. So we introduce what we call random variable. That was an M, sorry. Random variable. And usually we use a capital letter like an X or a Y to represent the outcomes. So the possible values of x, and it's just a way to write fewer words. The possible values of x are 2, 3, 4, the outcomes. So then this, the probability of outcome 2, we can write as the probability with a p of x equaling 2. It's only there to just for convenience, to shorten the things we are writing. That's all. We're not changing anything. We're introducing this x to just allow us to write fewer words. That is all. The probability of getting an outcome of 3 is the probability of x equaling 3. So for each value of x, there is an outcome and therefore a probability of that outcome occurring. Let's go, I'm not going to list all of them because there's a fair number of them. Let's, for example, look at, so among the probabilities, we might have the probability of x equaling, let's go with 10. Each one of them will have a probability. Let's just pick one. We don't have to do them all. So out of the 36, I'm only going to count how many pairs will get me, when I add them up, an answer of 10. Well, certainly 5, 5, right? How else can I get it? 6 and 4, and therefore 4 and 6. Can I get it any other way?
No.
If I want to use a 3, there's no 7. So that's it. So 3 of them. So again, a different number of ways, and those guys aren't equally likely at all. 3 out of 36 will give me a sum of 10 when I add the two numbers. And then, of course, you can go ahead and list them all, but I'm just introducing this x. We don't want to have too many options because it just gets tedious, and we get the point. The x equal to 10 is just a short way of saying the event that I get a 10 when I add up the two numbers that I roll. It's just for convenience. Any questions so far? I'm not setting you up for something more complicated. This is just what it is. Let's look at our example lab space or exercise 7.1, where we look at something that doesn't have that many options, just to make it a little bit easier. Now notice the difference between our previous example and this one. Here we also have an experiment consisting of rolling 2 dice. But what I write down on my clipboard is different. And therefore, in its entirety, it's a different experiment. Even though the first part of that action is the same. I roll 2 dice, and I note the largest number that appears. So I am doing something different. It is technically a different experiment, even though it still starts with 2 dice. They define the random variable x for me, and it represents, this is at the top of page 50, the largest number among the 2 rolls. So I need to understand what is the action and what is written down as results. Right? That together makes the experiment. So my possible values of x is just another way of saying what are all the outcomes I could get, what are all the things I could possibly write down on my clipboard when I'm doing what they say I should do. What is the smallest number I could get?
1.
How do I get a 1?
1 and 1.
1 and 1, largest number, 1. Can I get a 2? Can I get a 3? How high can I go? I'm only going to go to 6. So it's a different random variable. It has different potential values because something else, even though it started with 2 dice, something else was happening. What I observed and wrote down was different, and therefore everything's different. Everyone happy with 1 to 6? Okay, well, happy is maybe too strong a requirement. Does everyone agree with 1 to 6?
Fantastic.
Number 2. Now I want to find all the probabilities. I only have 6, so it's going to be okay. But we're going to do this in a table format to make it a little bit easier. And I'm kind of doing 2 and 3 together. But it's okay. So we could say, let's say here, maybe a column for the possible values of x. Let's write that as an n. N for number. And then the numbers could be 1, 2, leave some space because the probabilities are fractions, right? 4, 5, and 6. And I can do them all because I don't have that many, so it's okay. I didn't want to do the previous one. Then the other column is going to be the probability that x equals that number that I'm looking at. And it could be different numbers, 1 to 6. Does that make sense? It's Friday. You're coming off a pretty difficult chapter 6. So I want to make sure we're already losing 1.
No.
So I want to make sure chapter 7 doesn't pile more stress on top of this. Everyone happy how to read that table? Chapter 7 isn't here to add more stress. We're slowing down.
Like, so n, each time
Just
you
a
roll,
number.
or is it just like we're looking for numbers?
No, n is simply the possible things I could get.
Okay.
Yeah. And then I can get one of those things, and each one has a probability of occurring. They're not all equally likely. If I look at the possibility that x equals 1, in words that means the possibility of the two rolls giving a largest number 1. Well, I can have 36 possible pairs. I have to look at it like this because only these pairs are equally likely. These numbers are not equally likely. And if I make a fraction, it comes from equally likely results. How many pairs will give me an outcome of 1? Only 1. I have to roll 2 ones. There's no choice. So I can say here, the pair 1, 1 is the only one. Then I'm going to make lines here because they're going to get a little messy. Just to see how much space I have for my fractions. I left more space at the end, but these guys are a little squished. So out of 36, I'm trying to see how many will give me the largest number at 2. Well, 1, 2, or 2, 1, or 2, 2s. The largest number is in every case a 2. So there are 3 of them. So I'm counting, so those numbers all mean different things. In the first column, it's the number under the n column that names the outcome, names what I'm writing down as a result, the largest number that I get among the rolls. The numerator in the probability is how many different pairs will give me that outcome. And then I list the pairs. I just count them. There's no shortcut necessary. This is already so short. Listing them is perfectly fine for us. Any questions so far?
So if you don't assign like so like you have one dice is red, one is blue, and you use that. Now if both dice were white,
No,
would
I
that-
need you-
would that change like completely?
There's some technicalities that make things a little tricky. When I need things to all be equally likely, I have to require that they are distinct. I can tell them apart. Otherwise, things aren't equally likely. And it gets a little messy. Yeah.
So
But I don't really want to
Does it mean-
go and open that door. We can't make that probability unless everything we're counting is equally likely. And if I have two dice that I can't tell apart, then they're not necessarily equally likely. Because I can't tell that I got a 2 and a 1 and a 1 and a 2. They look the same to me. So they're a little more likely than two 2s, which can only happen once. A 2 and a 1 can happen two ways. And if I can't count those separately, I can't make that probability fraction accurately. Yeah. It gets a little tricky when you work with identical things. Yeah. But that gets a little complicated really fast. So I'm always just going to make them distinct so that every pair is equally likely and I can just count them and list them. But no, there's a lot more under the surface. It never stops. Yeah. So if I'm now looking at the third column, n equal to 3, that means I'm looking at the outcome of the largest number among the rows being 3 out of a possible 36 pairs. How can I get 3 as the largest number? I just list all the pairs. 1, 3, 3, 1. I can also get a 2, 3, and a 3, 2, and 2, 3. 3, 3. Nothing else can happen. So as long as there's a 3 in my row, and the other number is 3 or less, the largest one's going to be a 3. So in this case, I have 5 of them. 5 pairs out of the 36 will give me that result. Everyone happy with 5? And I just list them. We only have 36. It's not going to be that bad. And soon we'll notice a pattern if you don't already. Then I'm looking at the largest number being 4. How can that happen out of my possible 36 pairs? I need a 4 and something else. So I need a 4 and a 1, 2, or 3. But they can swap around. I can have a 1, 2, or 3, and then the 4. Or I can have 2 4s. So there are 3 of these, and another 1. Does that make sense? I'm just running out of space.
There's no symbol to say take the last thing and just flip them?
Oh, you can write this in any way you want. You just want to count and make sure you get 7. If you have a lot of space, list them all. But I'm starting to see a pattern. As long as I have that maximum number and lower stuff, so a 4 and 1, 2, 3, or the other way around, I can also have 2 4s. That's the only way I can get it. How you write it is irrelevant. I'm just running out of space. Then if my largest number is a 5, the same thing. Out of 36, I can get a 5 with 1 or 2 or 3 or 4 and flip them around. No, not the 5 first. 5 second, and then 1 or 2 or 3 or 4. Or I can get 5 and 5. So that should give me a 9, and the next one's going to be 11. But I do have to double check. How you list it, shortcuts, list them all in detail, doesn't matter. I need to consider how many of those pairs will give me x equal to 5, because x equal to 5 means 5 is the largest number among the 2 rows. Right, so I get that table, or those probabilities, just in table form for convenience. Table is nice for us. What happens when I add up all these probabilities?
36.
Whoops, that was erasing. Add probabilities together. What do I get? I get 36 out of 36. Does that make sense? That it should be 36 out of 36? Yes, because one of those has to happen. It doesn't have a choice. It has to happen. Something has to happen. And the only options for the largest number is 1, 2, 3, 4, 5, and 6. So my probabilities altogether have to add up to 1. Because something is guaranteed to happen. But you see clearly they're not all equally likely.
No matter what size dice you use, you just multiply them to get your total number that you're looking for, probability.
Yes. If you're counting in this way, which we always will. So there's a problem, for example, where the first problem, you have a 6-sided and a 4-sided die. So it's going to be 24 options.
And then you just know there's 24 options.
You can list them all, but it's always just going to be multiplication. Yeah. It's based on some fancier counting principles, which we are not going to do because that takes a long time to really understand. But yeah, you can just multiply them. Because if you look at the first roll and the second roll, the first roll has 6 options. For each of those options, there are 6 more. So if you imagine the tree, it's 6 groups of 6, which is multiplication. So it's not that hard to justify. So we are going to call this whole thing, this table, the probability distribution of x. X is really capturing the experiment information. And when I've listed all its probabilities associated with all its possible values, it shows how the 36 over 36 is distributed over the possible outcomes. Probability distribution. So now we're sort of dipping into number 3. I've done sort of 2 and 3 together. Number 2 asks for just list the probabilities, but I listed it in the table form, and that is answering the probability distribution in number 3. So I sort of did them at the same time. Table form is just nice. But there's a little more in number 3. I could visualize this with a graph instead, which is sometimes nice. Graphs are nice because it shows information sometimes in a more effective way. So let's just see what that would look like. So I'm going to have my vertical, whoa, that was supposed to be a straight line. Vertical axis, I mean that's big. And that's going to be my probability that x equals a number. And then I'm going to have my horizontal axis, the possible numbers for x. Because those are the 2 things in my table. And it's always going to be like that. The vertical one is going to be the probability. Now, I'm going to have my possible numbers, which were 1, 2, 6. Let's just center them like this to try and space them perfectly, but that's probably not going to happen. Like so. And then, to make it visually more appealing, I'm just going to put little columns or little bars centered at the number. So these are just going to be my separation of the bars that I'm trying to space out and plan for myself. So my first probability, or my probabilities go from 1 out of 36 to 11 out of 36. Now my scale is going to be a little messed up. Let's say this is 11 out of 36. Ooh, let's break this up into 11 pieces. That's going to be tough. If you have a ruler, it's a little easier. That is not done very well, but that's okay. That was supposed to be 6, actually. Try and break this up into 11 equal pieces, which is a little bit of a hassle because 11 is not an even number. But with a ruler, it's not so bad. I think that's 11. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. Good. So this bottom one is 1 out of 36. I'm not going to write every fraction because I don't have a lot of space. But let's write maybe the middle one there. 1, 2, 3, 4, 5 out of 36. It's over there. 6, 7, 8 out of 36. It's over there. And so like that. So the first bar is going to be over here with a height of 1 because that's the corresponding probability. Next probability has a height of 3 out of 36. I'll try and make these perfect. 3 is over here somewhere. Then it was 5. Like so. Then it was 7, which is roughly over here. Then it was 9, and I'm just eyeballing this. And then it was 11. Like so. That's not bad. So there's the graphic, and there are multiple ways to do the graph. You can have a line connecting them. You can have bars with spaces between them, whatever. It's all essentially the same information. For our purposes, it doesn't matter. We have a more visual representation of how the probabilities relate to each other, which in many cases is nice to see instead of this table. You can't necessarily look at this table without really thinking about the numbers and how they compare. This is visually much more, much easier to interpret. So just different ways to represent the same information, how the probability is distributed across the possible values. Scratch out in number 3 the formula. We're not going to do that anymore. There's no need for that for our level. So this is number 3, second part. It can be a table, it can be a graph, it can be both. Depends on your goals, what you're trying to convey to your reader. Graphs are often used. Then the number 4 is just asking me to highlight the 2 main features of the probability distribution. And the first one is that the probabilities add up to 1 or 100%. And the other one is they're all probabilities. Each probability is between 0 and 1 because it's a fraction, a little fraction. I can't have less than 0 out of 36, and I can't have more than 36 out of 36. I only have 36 options for my pairs in the counting. All right, any questions on the graph? Should I look back at the table? If you want to make sure your notes are accurate. Anything at all. Is it okay so far? No. Not so bad. You just count some dice.
I was just going to say, let's do poker.
I'm going to leave that for the portfolio assignment, but we do need Monday to just clarify that portfolio assignment question. I'm only doing half of chapter 7 because I don't want to rush the second half.
So if you have 2 decks of cards that you're mixing together and you're laying 2 out and you're trying to find the probability of getting like a third card, would you multiply the 52 by 52?
No, it's much more complicated. Much more complicated. Yeah. Because you're making selections of cards and the order actually doesn't even matter. You're not, it's much more complicated. There's no quick way to explain that.
Save it for Monday.
We are taking a shortcut on that because the actual topic to get to that point will take at least a week. And I removed it because we just don't have time. I'd rather focus more on geometry. Because that level of counting, you'll never do. They removed it from high school. It doesn't even get done anymore. So it's not even elementary school level. It's much more complicated. But we can still get the point across with our shortcut. I just have to do it on Monday. So, 2 more exercises and we're done for today. You could Google it, sure. Just be careful when you look at Wikipedia. Wikipedia gets complicated really fast. It's all correct, but very, very complicated. 7.2. For a weekly raffle, 1,000 tickets are sold at $2 each. There's one first prize of $100, 2 second prizes of $50 each, and 7 third prizes of $20 each. Determine the probability distribution associated with your net winnings if you buy 1 ticket at random. So they tell me, sort of, but what the variable in question is and what kind of outcomes I'm looking for, but I kind of have to define it specifically. Let X represent your net winnings. I won't say all of it, from 1 ticket. That's the only thing we're doing. Then usually we want to write what are the possible values of X. Let's start with the best case scenario. Best case scenario, I win $100. What is the corresponding value of X that matches that result?
98.
It's 98. What I'm really winning is $98. And it's based on, because I've chosen X to represent your net winnings, your profit, because that's what they use in the question. If you define X a different way, then the values will be different, but this highest value will still correspond to me winning first prize. So I just want to make sure everything matches up. Next best is second prize of $50 each, and then X will equal 48, the actual profit I'm making. Next one will be 18. Is everyone happy why those are the numbers? Because I decided to let X represent the profit I'm making. Then I have to go with that choice forever. I also have to make sure that I'm listing every possible value of X that can happen, meaning every possible thing that can happen, possible result.
-2.
Yes, I could unfortunately lose my money. And that is not covered here yet, so -2. Then we are ready to find the corresponding probabilities, and there are only 4 outcomes. So my probability distribution, we will stick to the table form because it's more than sufficient for us. I have my possible X values, and then the possible, or the probability that X equals that number. Just a fancier, more compact way of saying all these words. 98, 48, 18, and -2. So when I look at the best case scenario, which is represented by this 98, it's winning the first prize. Well, out of a possible 1,000 tickets, I'm going to have to pick the winning ticket to get first prize. So my chances are 1 in 1,000. So these probabilities aren't designed to be super complicated. You're just setting up all of the options and their corresponding probabilities. Everyone happy with 1 in 1,000? Second prize? which is represented by 48, there are 2 second prizes. So if I pick any of those 2 tickets out of 1,000, I'm going to win that. And the third prize, there are 7 of them. And not winning anything, actually losing, has to be the rest, because I know this has to add up to 1,000 out of 1,000. So it has to be 990 out of 1,000. Whether I can count them all or not, it's really sort of doing it in reverse. It has to be everything else. That's a property of the probability distribution, that the probabilities, if I have them all, they need to add up to 100%. That wasn't so bad, I don't think. No? Yes?
That's all the questions.
That is all the question. I'm going to add a little bit, because why are we doing this? There's a reason why. If you, for example, want to set up this raffle and you want to figure out, is this a good game? Am I going to make a profit? What's going to happen? Am I going to lose money?
No, you're gonna make some.
How do you know, though? It could be a much more complicated situation with more options, right? How do you know you're making money, and how much money?
Are you selling, is it guaranteed to sell the 1,000 tickets? Do you have that?
Let's suppose yes.
So you can make $2,000 and then you're paying out 100 plus 50, that's 150, 7 times 20, so 140.
I know that, I understand that you believe in what you're saying, but I don't have your confidence. Why is $2 enough to charge? Should we maybe charge them $2.50?
Yeah, so.
Is $1.50 okay? We don't know.
Depends on how much tickets cost to print. If you get a good.
No,
deal,
you're-
things are $500.
That you're trying to catch me in a technicality. That's not the point. We're keeping things simple.
That's called a variable.
Oh, all right. So we have what is called the expected value. Lunchtime is, well, not soon, but you can have an early lunch. Expected value of x. And we're going to name it E for expected value and then just a variable. And it gives me a way to have a number that I can put on what do I expect is going to happen. Hence expected value. Now here is the formula. It's not the easiest thing to explain why, but we can just use the formula. I'm going to take each of the numbers, the values of x, and I'm going to multiply them by their corresponding probability, and then I'm just going to add them all together like that. So the number times its probability, the number times its probability, the number next times its probability, and I just keep going down the line. Now the next one is a -2, so I need to incorporate that negative. And I'm just going to go through. So in this way, the results are weighted according to the probabilities. Something that's more likely gets a bigger say in that calculation. By multiplying by the probability, it's sort of the weight that that result carries. No best explanation. What do I get when I calculate this? It's not the hardest calculation, but I want to see what I get. You have it all figured out. So without expected value, this is all kind of pointless. It's there as the final step to analyze this raffle game and see, is it profitable? For which side? How much? Do I need to make adjustments? Should the first prize be bigger, smaller? Should the ticket price be more or less? Those are valid questions. What do I get? Someone should get something.
-1.66.
1.6 repeating, so 6, 7.
It's just 6.
Oh, all right. I was guessing. What does that mean? This has to tell me something. Well, the expected value is going to be interpreted as follows. If we play this game, this raffle game, repeatedly, forever and ever and ever, then by buying one ticket, then we are, let's say, our net winnings, because that's what X is, our net winnings will average to, this is in dollars, let's say, negative 1.66. So I could play this raffle and maybe I win first prize. Should I keep playing? No, because this says long term I'm going to lose eventually that whole $100. It'll just get chipped away slowly if I play long enough. So it's good for the host of this raffle. It's not a good game for me long term. If I win, maybe just walk away. But that analysis tells me how to approach it. Depends on which side I'm approaching and so on. So if the player long term loses money, that means this is profitable for the host. And the expected value tells me that long-term average. Long-term average that I could expect. And it also gives me an indication. If I were to play, I don't expect to win. It could happen. It's not likely. Because this probability associated with winning was so small, it doesn't have a big part in this calculation. Okay, let's try and squeeze in one more, because there is another exercise. No, not sign. More exercises are good.
No, fine, because it's almost done.
Oh, sure, sure. End early? No, that's not right. Consider the following game of chance. 2 balanced 6-sided dice are rolled. If double sixes are rolled, the player wins $10. If doubles of any other number is rolled, or are rolled, the player wins $5. But if 2 numbers on the dice are different, the player doesn't win anything. On a single play, what's the probabilities? And so on. So, we are going to say, let X represent the, let's call it the payout, how much you're going to win. I don't know what the ticket price is going to be in this case. They don't tell me. The possible values of X will then be $10, $5, or no dollars. The only things that can happen. As a player, or as a host, I'm either going to pay the player $10, $5, or nothing. So then my distribution are the probabilities over these values, 10, 5, and 0, will be, well, how can I get $10? I'm rolling 2 dice. So 36 possible pairs. The only way the first prize is happening is the one case where it's 2 6s. So there's only 1 in 36. For the second prize, they're going to have to roll doubles of another number. So 2 1s, 2, 3, 4, 5. Because the 2 6s are done. So there are 5 possible pairs that will get me that. And the 0 case is everything else. So it has to be 30 out of 36. If we now calculate the expected value of that, it's again the number times its probability plus the next number times its probability plus, I'll write down the 0, but it doesn't actually feature in the calculation because it's 0. I know we're doing this one a little fast, but the more we do now, the more open next week's going to be. It's going to be wide open. I want to be done by Tuesday, which means that's my goal. Maybe Tuesday with a little Wednesday.
I get this
That gives us most of Wednesday, if not all, Thursday, Friday, and the next Monday. You're welcome.
Thank you.
So it feels bad now, but it's gonna be okay.
Friday learning.
You know, Fridays are hard. Not easy. This week was full. Full. What do we get? You don't have to actually calculate the zero part, right?
35 over 36.
Decimal.
0.9722.
0.97-ish. What does that mean? That should tell me something. The whole point of this is that it conveys some information about how this game behaves. So I'm now pretending to be the host, and I'm planning this game. I don't know what the ticket price should be. If I do this without any ticket price, and actually pay a full 10 and a full 5, I'm going to average out over many, many games, paying 97 cents every time. So as long as I charge people more than that, I'm going to profit long term. Now I can decide how much. If I just charge $1 to play, then I'm going to make 3 cents every game. And if I play enough, it's going to add up. If I charge $2, then I'm only going to pay out 97 cents, but get $2 per game. So I'm going to be up. This is the long-term average payout per game if the games are many, many, many. It only stabilizes many times. If I play once, if I host the game once to one person, I might have to pay $10. But if I host it long enough people play, I'm eventually going to stabilize at that. So then I can adjust my ticket price accordingly. So the expected value is a way to analyze these games of chance that can be very complicated. And unlike some people, my intuition can't say that this is a balanced and a good situation without some analysis.
Please remember to click the like button if you enjoyed the video, and to subscribe if you want to be notified of more videos. Thank you.